Hi, my name is Chris Harris and I'm from AlleryTutors.com, and welcome to this video on the CIE past paper, and this is paper 5, so this is the one that's all on planning, analysis and evaluation, so it's like the kind of like practical technique side. For your information, this paper is 9701/51, so that's it there. This is the paper that we're going to do, and this is the October-November 2014 paper. And the whole point of this video is to go through the paper and to hopefully give some little hints and tips on the way of how you work these things out, because obviously you have the mark scheme, but the mark scheme actually doesn't tell you the actual answers. Well, it does tell you the answers, sorry, should I say, but it doesn't tell you how you've worked out the answers, or crucially explain why they are the answers as well. So the whole point of this video is to obviously go through that as well. So if you can get a hold of this paper, then you'd be able to go through the paper yourself and then check back in this video to find out the answers and obviously to find out why as well. Right, okay, let's make a start. So starts with question 1. There's two halves to this as well, and also I should say that with the answers that I might get on here, you might get slightly different ones, because obviously it does depend on, in particular in question 2, there'll be a graph. It depends on how you've drawn your graph, so if the numbers don't exactly match what I've got, that may not be a problem. Just make sure that the method that you followed is the same as what I've done. You should get your marks that way. Okay, so this is question 1. It says, a solder is an alloy of metals which is used to join other metal pieces together. A specialist solder that can be used to join pieces of aluminium is made from a mixture of mass of 65% zinc, 20% aluminium and 15% copper. You are to plan an experimental procedure to confirm the composition of a powdered sample of this solder by adding reagents and then extracting from the mixture each of the following in sequence. So copper metal must be extracted first, the aluminium as aluminium hydroxide, and then the zinc as zinc hydroxide. So they've given you a little bit of structure there. And you are provided with a sample of this solder with an approximate mass of 4 grams, okay? 1 moles per dm cubed sulfuric acid and 1 moles per dm cubed ammonia as well. No other reagents should be used, so this has kind of helped you a little bit because they've told you what reagents we're going to use. Standard laboratory equipment is available, including a balance accurate to 2 decimal places. And it says, for part A, it says complete the flow chart below to show the order in which the reagents would be added to the solder to allow you to extract and separate the components as copper metal in step 1, aluminium hydroxide in step 2, and zinc hydroxide in step 3. You are reminded that aqueous ammonia contains both the base OH- and the complex forming molecule NH3. Okay, right. So let's scroll down. Let's see what we've got. Okay, so it says step 1. It says the reagents are added. Now, we were told earlier that we have to extract copper first, and we have all these other metals as well. Now, the first thing you can do is we have aluminium and we also have zinc as well. So when we react these things together, what we can do is we can add sulfuric acid, because actually what will form if we add sulfuric acid to this alloy is actually 2 of the metals will dissolve, and they form a soluble solution of zinc sulfate and aluminium sulfate. Now both of them are soluble, so you do need to know that. Copper isn't soluble unless you're using heat and concentrated sulfuric acid. Copper really doesn't dissolve with the sulfuric acid. Now that can be a benefit because obviously there's a method in which we can eliminate 2 of the metals and get 1 metal on its own, and this one is obviously copper. So the first reagent we're going to add, and we're going to add this on here, is sulfuric acid. There you go. And the substance present at the end of the reaction, well, what we're going to have is we're going to have zinc sulfate that's formed, because the zinc will react with sulfuric acid and it'll form zinc sulfate. So we're just going to add that on there. Zinc sulfate. Okay. And then we're going to also have aluminium sulfate as well. There we are. And obviously we're going to have copper as well. And the copper won't react, like we say. All right. Okay. So what we can do is we have zinc sulfate and aluminium sulfate. Both of these are in solution. Copper is solid, so we can filter it. And obviously the bit that we have left in our filter paper is going to be copper, because that's going to be a solid. So there we are. We've actually separated our first metal. So now what we have to do is we obviously have these two solutions now. We have zinc sulfate and aluminium sulfate. And we need to try and separate them as well. Now the chemicals that we had, remember right at the start, it was saying, is that we had ammonia as well. And actually when we react zinc sulfate and aluminium sulfate with ammonia, we have a reaction with both of them. But they both react in a slightly different way. So for example, with the zinc compound, when we react that with ammonia, what we have is obviously we add the zinc sulfate, there's water in there as well, so we have our zinc hexa aqua complex, and then when we add ammonia to that, 4 of the water ligands will drop off, and we have a ligand exchange with excess ammonia. So we have lots and lots of ammonia, we have a ligand exchange. But with aluminium, the ammonia actually acts as a base with aluminium, and what it does is it removes protons from the aluminium, and it will form a hydroxide instead, mainly because the Al3 plus aluminium is much more acidic than your zinc complex, so the ammonia acts as a base. So we're going to form two substances here. So let's just write this down first. So the reagent here is going to be excess. So we said excess ammonia. There you go. And so the substance is present at the end of this reaction. So when we take the zinc sulfate, which is one of the products here, the zinc sulfate, when in water, will form your zinc. Obviously, this is zinc sulfate, so it's soluble, so it will form your zinc hexa aqua complex. And when we react that with ammonia, and it's excess ammonia, then what we get is a complete ligand exchange. And well, not complete, but we get 4 of the water ligands that drop off, and so we form zinc tetraamine molecule. So we're just going to put that there. Zinc tetraamine. Okay, so this is your ion, remember? So effectively, let's just quickly, if I just draw a little molecule here. So we have water on there, and then what we have, remember this is zinc 2 plus, and then what we have is the NH3s on this side. Let's literally try to squash this in here. Go. So the whole thing, water's neutral, a neutral ligand, so that's not really going to have an effect, and so is ammonia. And so what we have is a charged complex, which is this molecule here. Now, because it's charged, this means it's actually in solution. Remember, complexes which are neutral, the whole complex, which is neutral, which doesn't have a charge, will form a precipitate. So because this one is still charged, 2 plus, this is actually still going to be in solution. So that's really, really important, and that's crucial to understanding what's going on here. As with the aluminium, like I say, the ammonia acts as a base with an aluminium instead of a ligand, and that's something you're just going to have to try and remember. The aluminium is a 3 plus, so it's more acidic than your zinc complex. So I'm just going to put here, what we form is aluminium hydroxide. Now, if we had to draw that as a complex, I'll just draw it here. So aluminium it could be something like that. OH, water, and then another OH. There you go. So the reason why we have 3 OHs is because this complex here, if we add just enough hydroxide, effectively, what will happen is the OH has got a negative charge. We have 3 negative charges, 3 OHs surrounding it. Aluminium has got a 3 plus charge, so water has no charge. So if we add them up, we should get a whole complex that has no charge, no overall charge. And so that means if it has no overall charge, it doesn't dissolve in water. We actually get a precipitate that's formed. So now we have 2 solutions. We have this zinc one here, which is in solution because it's charged. And we have this one, the aluminium one, which is a precipitate, so we have a solid. And so for that reason, what we can get is aluminium hydroxide, and that's what we have there. So there you go. Okay, so there's our next substance there. So that's quite a tricky one. There's all this kind of ligand exchange and transition metal chemistry. Okay, and then on to step 3. This is the reagent added. Obviously now we have our aluminium hydroxide. All we have left is our zinc tetraamine complex, which is in solution. So then what we have to do is we then need to add sulfuric acid back again. And what that'll do is it'll pull off the ammonias or the amines or the NH3s that are on your zinc complex and form ammonium sulfate, and the waters will actually take the place of the ammonia that was there. But crucially, we know that the product here must be zinc hydroxide because it told us that in the question. So actually, some of the waters obviously have been converted into OHs because we form in zinc hydroxide, and that must be a solid as well because it has to be removed by filtration. So we know our final complex has got to be a zinc complex with no overall charge because it's got to be solid, and so therefore it's got to be zinc hydroxide as a product. So that's how we know that. But the only way we remove them ammonias from there is by using sulfuric acid. So we're just going to put that on there. Sulfuric acid. Okay, substance present at the end, we have ammonium sulfate. There we are. Okay, so that removes the ammonia, and then we have zinc hydroxide. There you go. Okay, and the substance removed, again, has to be zinc hydroxide. Okay, so we get 5 marks for that. So it's not too bad, really. You need to know your transition metal complexes and your transition metal chemistry for that one. So there we go. Right. If you don't, you need to really look at that. Okay, so B, it says for some of the steps in the procedure, you would need to be careful to add an appropriate quantity of a reagent. Now, that is really important. It says for each step of your procedure, explain why particular quantities of a reagent should be chosen, should I say. Right. Alright, okay, so let's look at step 1. So step 1 was the addition of sulfuric acid. So if I just go back there it was there. So addition of sulfuric acid. Now, what we have to do, the reason why we added the sulfuric acid is we wanted to dissolve the zinc and aluminium. So you just need to add enough just to dissolve the zinc and aluminium, and you should have some copper that's left behind. So effectively that's all you need to put for step 1. So just need to put enough sulfuric acid to dissolve zinc and aluminium. Okay, so we just needed to add enough just to do that, really. Okay, step 2. Obviously, so we need to look at the reagent for step 2. Step 2 says we're using excess ammonia, as you can see here. So we're going to add the excess ammonia. Now, we're going to add enough, again, to make sure that we get a precipitate of aluminium hydroxide. So we don't want to add too much, otherwise we might redissolve this again. So we just need to add just enough to get this precipitate to form here. And we need enough as well to dissolve the zinc hydroxide, which is the substance, obviously, that we're going to form here as a result with the excess ammonia. So so we need to effectively make sure that we add enough to form aluminium hydroxide, this precipitate, but enough to effectively get rid of this as well, this zinc hydroxide. Because remember, the ammonia can act as a base, so we need to keep adding until we've got to this state here. So we've got ligand exchange. Okay, so let's just go back. So step 2 is we need to add enough now this is aqueous add enough aqueous ammonia to precipitate so to form precipitate of aluminium hydroxide. There you are. Okay, so but we need to make sure that we have our zinc substance that's actually completely disappeared. So our zinc hydroxide in particular, we need to add more to make sure that disappears. Otherwise you could get zinc hydroxide as well, but adding excess means that you can effectively have ligand exchange and you get that ammonium complex that we talked about there, which is the zinc ammonia complex. So if we add excess, it means we can get this ligand substitution instead of it just picking off the protons. So yeah, so we'll put that down as well. There we go. Okay, and step 3. So again, with step 3, what we're doing is we're adding sulfuric acid this time. But what we've got to do is, because if we think about in this one here, we are forming ammonia. We have some ammonia left over in our solution here, and obviously the ammonia is on the Zn2 plus as well. Now, what the sulfuric acid is going to do, we're going to need to add enough of this to neutralize the ammonia. So to kind of remove all these ligands here, and we need to add obviously enough to get your precipitate of zinc hydroxide by removing these ammonias from here. But we don't want to add too much, because if we add too much of this, then our zinc hydroxide, which is zinc with the OH2, so 2 of the water ligands are OH. If we add too much of that, then what can happen is the zinc hydroxide can actually dissolve. So it becomes soluble again because of the additional protons that we've got here. So we've got to balance it. So we've got to add just enough to neutralize the ammonia that's been kicked off the zinc, but not too much, so that the zinc hydroxide will actually then dissolve back into solution again. So yeah, it's like a drop by drop basis, and you've got to be really, really careful with these. Okay, so step 3, let's write this down in here. Okay, so what we put there is we need to add enough sulfuric acid to neutralize ammonia and to precipitate your zinc hydroxide, but not too much that the zinc hydroxide dissolves, because obviously if we did that, you would be back to square one. You just have 2 solutions. So let's just add that on there. Okay, so marks. We get 1 mark for that, 1 mark for that one. We get 1 mark for saying that we need enough to neutralise the ammonia, but not too much so that the zinc hydroxide redissolves again. So you get 4 marks in total there. So, okay, not too bad. Right, part C. It says the aluminium hydroxide and zinc hydroxide that have been extracted are difficult to dry, so it's better to convert them to their oxides. Describe how this could be done and how you would make sure that each hydroxide has been completely converted into its oxide. Right, so the way in which we can do this is really straightforward. If you want to form an oxide of something, we effectively can just heat it, and we take these metals here, these hydroxides, and heat them. That obviously reacts with the oxygen in the atmosphere, and we form our oxides. But to make sure that we have all of it has been completely converted into its oxide, we are basically looking for a constant mass. So after heating it for, say, like 5 minutes, you weigh it, you heat it up again, and you weigh it. And if the second weighing as the first weighing is exactly the same mass, then you know that you've converted all of your hydroxides. So you need to heat it for a reasonable amount of time, but it is important that you need to keep weighing, otherwise you'll never know if all of it's been converted. So yeah, so that's what we're going to put. So heat them both. Until a constant mass is achieved. Okay, so we get 2 marks for that as well. So we need obviously 1 mark for saying heat them to get your oxygen, and then 1 mark for saying until we've got a constant mass is achieved. Okay, right, on to the next part. Okay, so the purpose of the experiment is to confirm the composition of the solder. When the experiment is carried out, state the measurements that would be taken and what you would do to the copper to make sure that the correct value is obtained. Right, so what we'd have to do with this, obviously, like it says, the purpose of the experiment is to confirm the composition of the solder. And right at the start, it told us that the composition was actually 65% zinc, 20% aluminium, and 15% copper. So this is by mass. So obviously, if we're weighing these things, we have to make sure we measure the mass of the copper that we formed in step 1, the aluminium hydroxide that we formed in step 2, and the zinc hydroxide that we formed in step 3. Or what we can say is, if instead of aluminium hydroxide, you could say aluminium oxide, because remember we have to convert them to oxides, or zinc oxide as well. And obviously the solder. Because they said the solder was just approximately 4 grams. So we need to take an actual reading of the solder and then take the masses of each individual compound that we formed. So let's write that down. Okay, so we're measuring their masses, obviously, because we're going to work that out. And then what would you do to the copper to make sure the correct value is obtained? What you'd have to do is you'd have to rinse it. You have to wash the copper. The copper may have some impurities on there because you filtered it, obviously, from zinc sulfate and aluminium sulfate. So you might have some residual chemicals that's left on the zinc. So you'd have to wash it, and then crucially you'd have to dry it, because if you didn't dry it, you'd have the mass of the water on the zinc as well, on the copper. So you'd have to dry it as well. So that's the answer to that bit. So the second bullet point is the copper should be washed and dried. Alright, okay, so we get 2 marks for that. Obviously 1 mark for the first step, 1 mark for the second step. Okay, says if the mass of aluminium oxide obtained was 1.50 grams, calculate the mass of aluminium that was present in the solder. Right, so okay, so what we have to do, it's only for 1 mark, so there isn't a massive amount of calculation to do here. What I would do is write down the formula for aluminium oxide. So the formula is Al2O3. Okay, and what we need to do is we need to work out the relative atomic mass of the individual parts of the aluminium oxide, and from that we can work out the relative molecular mass. And then once we know the relative molecular mass, we can then work out obviously the mass of aluminium individually. So if we use our periodic table, oh actually we don't need to, because we've got the masses here. So we've got aluminium, 27, but we have 2 aluminiums, so we need to put 54 there. So I'm just going to draw an arrow there. That's 54. The oxygen is 3 times 16, and 3 times 16 is 48. Now if we add them up, we should get a mass of 102. Now we can say that's effectively like 102 grams. So in 102 grams of aluminium oxide, 54 grams will be aluminium and 48 grams will be, whoops, that's not a state symbol, that's a mass. 48 grams will be oxygen, and that would constitute the full mass of 102 grams. Now, we don't want to know what 102 grams is, we want to know what 1.5 grams is of the aluminium oxide. So we're going to put 1.5 grams there. Now, what we need to do is work out what do we need to do to get from here to here. So we're obviously going to have to divide this, and actually by working this out, if we do, you can put this in your calculator and it should come out with the multiplier. But if you put in 102, which is this one here, and divide that by 1.5, it will tell you what the multiplier is, and the multiplier comes out at 68. So what we're going to put here is effectively, if we take 102 and we divide that by 68, we should get 1.5 grams. Now we want to work out what mass of aluminium was present in the solder. So all we do is we go to this side, we do exactly the same on that side, we divide that by 68, and what we should get is a mass of 0.794 grams. There you go. And this is remember this is for aluminium, so that's why we took that 54, because we want to work out the mass of aluminium. So that's 0.794 grams that we have there. And obviously that just gets you the mark there. So that's 1 mark. Okay, and then on F, it says even if the experimental difficulties of extracting all the copper from the mixture was overcome, it would be difficult to obtain an accurate mass of copper from this experiment. And we're going to suggest why. Okay, so I mean, if you look at the start, the amount of copper that we're actually trying to extract is 15% copper from something like 1.5 or 1. Or from like 4 grams, effectively, or roughly 4 grams, we think. So that's pretty much going to leave us with a very, very, very small amount of copper. It's really difficult to get an accurate value on the mass of copper from this experiment, because the original mass is only 4 grams anyway. So that's going to increase our error, effectively. So yeah, so the reason why is the mass of copper is so small. And there we go. So we just get 1 mark for that. And that is the end of question 1. So you can see we get 15 marks there. I suppose in summary, you need to know your transition metal complexes here. There's a lot of stuff to do with the reactions of transition metal complexes. So make sure that you really do know them and you understand what's going on, because they are obviously pretty useful and they're pretty crucial as well for your exam. But it wasn't such a bad question, all in all. Not much calculation in there, just the one really. But on to question 2. Okay, so this is question 2. Question 2 says the acid dissociation constant Ka of a weak monoprotic acid Ha is to be determined from the measurement of the pH change that occurs when it is titrated with an aqueous solution of sodium hydroxide. 2.70 grams of HA was dissolved in distilled water to make exactly 250 centimeters cubed of solution. 25 centimeters cubed of the solution was pipetted into a beaker. This is such a classic question. Okay, and it says the pH of the acid in the beaker was measured and recorded in the table below. A burette was then filled with aqueous sodium hydroxide, and the 25 centimeter cubed of HA was titrated by adding volumes of the aqueous sodium hydroxide to the beaker as indicated in the table below. It says after each addition the pH was measured and the value was recorded. Right, so they're giving us a table of data, and you can see we've got the volume of sodium hydroxide that was added in centimeters cubed over here, and we've got the pH that's been measured, and this is obviously it run down here. Now, this is very, very common of them to ask them to draw a graph in the second question. So obviously they're giving you data and you need to plot a graph. Now, for speed, I've already plotted the graph already, because it says plot a graph to show how the pH of the mixture changes with the volume of added aqueous sodium hydroxide as shown in the table. So you draw a smooth curve. I've tried to draw it as smooth as I can with the limitations that I've got on this. It says using the plotted points on your graph to produce a titration curve for the addition of aqueous sodium hydroxide to the acid HA. Right, so this is my graph. Your graph may be slightly different. Now what I'm going to do is I'm going to just zoom out so we can see the actual graph. Maybe it's a little bit easier. There it is. So we should get a graph that's this classic S shape. So this is your typical titration curve, I suppose. And that's what it should look like. Now you need to make sure your plots are plotted accurately, and that you have a curve that goes through the points that you've plotted, obviously omitting any anomalous points as well. So as long as you've drawn a graph that looks like that, and the end point should be around about the 30 mark, then you will get both marks. So you need to make sure that you've done that correctly as well. Okay, so let's just zoom back in again. Okay, right. Let's just full drawing. All right, I'm just going to zoom in a little bit further just so we can get a good view of this. Okay. Right, so there's our graph there. Right, and then it says, I'm just going to zoom in one more time just to make sure that should be better. Alright, okay, so obviously there's our graph. There it is there, that's a bit better. Right, and then it says B, circle any points in the graph that are anomalous and suggest a reason why this might occur. Right, so I'm going to use blue. So we're looking for an anomalous result in our table. Now your anomalous result should be the same as mine if you've plotted your graph correctly. And so the anomalous result should come out at 12, which is here. Should be this one. There you go. There's your anomalous result. So just put a circle around it, and that would obviously get you the mark there. And then we have to suggest why this might have actually occurred. It could be a few things. You can see it's lower than the rest of them. So it could be something like sodium hydroxide. It may not have mixed properly with the acid, and so therefore it hasn't actually raised the pH by much. Also, you might have suggested that there might not have been enough sodium hydroxide added. Obviously, we've claimed to have added 12 centimeters cubed, but we might not have actually added 12. We might have added just short of 12, and so therefore it hasn't raised the pH high enough. Obviously, that cross should really be on that line there. So yeah, anything like that would do. I'll just put down. I'll put down one of them. So put the sodium hydroxide. If I can write properly, it had not been mixed properly. With the acid. Or you could say that not enough sodium hydroxide was added, or anything like that. So there you go. Right, so we get 2 marks for that. So obviously you get 1 for this bit, and then 1 for obviously identifying your anomalous result as well. So let's just put the 2 there. Okay, right. So it says, what would be the suitable range of pH values in which an indicator would change colour to identify the endpoint of this neutralization? Right. So if we go back to our graph, we're looking for an indicator which will obviously change within the vertical part of your titration curve. So in this case, we're probably looking at something, obviously it starts to really level off somewhere above the 6 mark. So somewhere around here, or like 6.5, somewhere around in that section there. So like this bit here. And then obviously it then goes up and it starts to flatten off at about like the 11 mark. It starts to curve back round again. So we're wanting one that changes between 6.5 and 11. Anywhere around there will do. So not 6.2, where that's come from. Right, so between about pH of 6.5 and 11, anything around there. It can't change, obviously, near the end point, near the points where it's curving, because that isn't really strictly the end point. So we need to make sure that it's well within that band there, that vertical band. Right, D. It says 30 centimeters cubed of aqueous sodium hydroxide is required to neutralize 25 centimeters cubed of HA, and the equation for the neutralization is shown. You can see here we've got the equation there. It says excluding water, state the 3 ions or molecules that will be present at the highest concentration when 15 centimeters cubed of aqueous sodium hydroxide had been added to 25 centimeters cubed of HA. Now it says here that we need 30 centimeters cubed of aqueous sodium hydroxide. 15 centimeters cubed of aqueous hydroxide is halfway to neutralization. So we call it the half neutralization point. And at the half neutralization point, what's actually happening is we have an equal amount of, obviously the sodium hydroxide reacts with the acid, HA, and that will form a salt. So what you would have is you'd have equal amounts of all these different ions, because we're like halfway there. So we'll have some of the acid, unreacted acid, which is left. Obviously half of it has reacted, half the acid has reacted, because when we get to the end point we don't have any acid left. It's been neutralized. So if we're halfway to neutralization, we'd have some unreacted acid, which is HA. You would also have obviously the products of salt as well, and because half of your acid has been has reacted, it will react to form the salt, and the salt dissociates fully to form its ions. So we'll have the ions of the salt that was formed as well. Again, we'll have equal amounts of the salt as we do the acid. So the salt is going to be the Na plus and A minus, because we don't know what the A is. Obviously, we're looking at A minus. So we'll have equal amounts of these. This will dissociate, which is the Na plus and A minus, and obviously we'll have an equal amount of HA as well. We do have water, but we're excluding that, so we don't need to worry about that. So the ions present are Na plus, we have A minus, and we have HA, because it's the half neutralization point. So make sure you understand the half neutralization point and what's going on as well. Okay, and then it says state and explain how the concentrations of these ions or molecules compare. Right, well, we already mentioned this already. So actually we'll have equal amounts of all of these in the solution. When we add more sodium hydroxide, this eventually will go down further, and these two will go up when we add more. But at the halfway point, obviously we have equal amounts of each. So yeah, let's write this down. So this is an assumption that we're making. So we will have nearly the same concentration of all of them. And the reason why is because half the acid, which is HA, has reacted with sodium hydroxide. There you go. So it's 2 marks. Obviously we get 1 mark for that bit there, and we get 2 marks for this bit here as well. So yeah, this again, it's called half neutralization point. So take a look at that if you're not too sure what's going on there. Okay, so E. So E says use your graph to determine the pH obtained when 15 centimeters cubed of aqueous sodium hydroxide is added to 25 centimeters cubed of HA. Use this pH to determine the value of Ka for HA. Right, now this is really useful. I'm going to show you this really little, kind of like this neat trick, I suppose, to make sure that you can get this right. And actually, you don't need to use the full Ka expression to work this out. So I'm just going to go back up though. Let's just find 15 centimeters cubed. We can see there's the 15 there. And we're going to go up to this point here, and we're going to go along. Now on my graph, this comes out at 3.9, a pH of 3.9. Yours may be slightly different. You've got to use your value here, but I'm going to use the value of 3.9. to give you an answer. As long as your method is the same as this, or you get the right answer according to your method, then you should be fine. Okay, so what we're going to say is our pH is 3.9. So let's just put that there. pH equals 3.9. Okay, that's my number. Now this is the half neutralization point, and at the half neutralization point, we make an assumption that the pH equals pKa. So I'm going to put that on there. Remember pH. pH is just the minus log of H plus, the concentration of H plus, and pKa is exactly the same, except it's the minus log of Ka. And actually what we need to work out is we need to work out Ka. So at the half neutralization point, the value of this will equal the value of that. And so because we know the value of this, which is pKa, we can then work out Ka as a result. And we can do this because we're at the half neutralization point. If we weren't, you can't obviously do this. But because this question is, then we'll make our lives a little bit easier. So I'll show you how it works. It's dead easy. So we'll put okay, so we're going to say at the half neutralization point, obviously this is what we're looking at, we can say that the pH equals pKa, which is just the minus log of Ka, and so therefore we can say that the value of pKa is going to be 3.9, because we say it's the same value as pH, and so therefore if we want to work out the Ka, we need to do the anti-log, or the 10 to the base of minus 10 to the minus 3.9 in your calculator. So so a way in which you can do that is if you press shift, which is the anti-log effect. If you press shift and then the log button, you'll see a little 10 on your calculator, and there's a little square in the top right hand corner if you get the same one as me, and then you just put in minus. You have to put in minus though, minus 3.9, and then obviously you'll get your answer. So if we put Ka equals 10 to the minus 3.9, that's what it should come out like on your calculator. It should come out something like that. Then obviously we should then get our answer to be 1.26 times by 10 to the minus 4, and this is in moles per decimeters cubed. Okay, so you get 3 marks for that. I told you it's pretty straightforward. You get 1 mark for working out obviously Ka, 1 mark for using this expression here, and then 1 mark for using your graph to actually work out the correct pH. So yeah, not too bad. Okay, and then it says F, use your answer to E and the initial pH of HA from the table to calculate the concentration of HA in moles per dm cubed. Right, okay, so what we have to do is we have to work out the, because we're going to use our Ka expression, and we're going to use the Ka expression to work out the concentration of HA. In order to do that, we need to work out the concentration of H plus ions. So what we're going to do is, we were told, remember, we were told the pH of the acid right at the start of the reaction. So if you look at your data table, let's just scroll back up and I'll show you what I mean. So obviously if we look at our data, there, right at the start, before we added any sodium hydroxide in, we had 2.41, that was the pH. So this is the pH of the weak acid. So if we take the anti-log of minus 2.41, we should get the concentration of H plus ions in this solution at this moment in time. Because remember, pH is measuring how many H plus ions we've got. So if we just go back onto here, so concentration of H plus equals 10 to the minus of the pH, which is 2.41. And then if we put that in our calculator, let's just bring it in here. So that is going to be minus 2.41. And we should get 3.89 times by 10 to the minus 3. Okay, and you should get that answer as well. And then what we do is we put this into our into our expression, Ka equals, now remember, we assume one of the assumptions we make is the concentration of H plus ions equals the concentration of A minus ions. So because it equals the same, we can assume that we put the squared bit on the top there, divided by the concentration of HA, which is your acid. So from that, we can work out the concentration of HA. If we rearrange this, we should have concentration of H plus squared divided by Ka, and that will tell us the concentration of HA. So let's just put that in there. So that's 3.89 times by 10 to the minus 3. All of that is going to be squared. Don't forget the squared bit. And I'm going to use my number, obviously, but you would use your number here for Ka in the bottom there. I got 1.26 times 10 to the minus 4, but you put your number in there. So your answer might be slightly different from this. As long as you followed this method, you should be alright. Concentration of HA. And then if we put that into our calculator, 3.89 times by 10 to the minus 3 squared, divide that by 1.26 times by 10 to the minus 4, and we should get a value of 0.12 moles per dm cubed. Okay, so you get two marks for this. One for working out H plus, and then one for working out your HA. Alright, and then part 2. It says calculate the initial concentration of HA in grams per decimeters cubed, and use this together with your answer from F part 1 to calculate the relative molecular mass, or MR, of HA. Remember that 2.7 grams of HA was dissolved and distilled to make exactly 25 centimeters cubed of solution. Right, so we need to work it out in grams per decimeters cubed first. Okay, so we're going to put that here. So the concentration of HA. Okay, and this is in grams per decimeters cubed. It's just another way of measuring the concentration of something. So this is going to be, now effectively we know the mass is 2.70, so I'm just going to put that there. However, this was the amount that was dissolved in 250 centimeters cubed. We need to work it out in a decimeter cubed. So a decimeter cubed is effectively 4 lots of this. And then we should work out the, obviously the amount in per decimeter cubed effectively. So this is how much we have per 250 centimeter cubed. But if we multiply that by 4, we'll get to a decimeter cubed. So we'll do exactly the same here as well. So it's 2.70 times that by 4. And that will tell us in a decimeter cubed, and that's going to be 10.8 grams per decimeters cubed. Just fitting that in there. Okay, and then what we have to do is then work out the MR. So this is the concentration in grams per decimeters cubed. So to work out the MR, we have to divide that by the concentration of HA, which we have here. That's that bit there. So all we have to do is we do 10.8, which is the concentration in grams per decimeters cubed, divided by the concentration in moles per decimeters cubed, which is 0.12. Whoops. And then that should get us 90 grams per mole. This is the units for relative molecular mass as grams per mole, because basically if we had a mass of 90, we had 90 grams of that would be 1 mole of any substance. You can see how you can work out the units here as well. Because if I take the units, this is grams per decimeters cubed, remember. This was the concentration here. And then the concentration in moles per decimeters cubed. So if I just put that there, moles per decimeter cubed. What we can do is we can actually cancel these out. We can cancel that one out and cancel that one out. And then what we're left with is if we take this mole and put this on the top line, we invert the sign in the top corner here, and what we're left with is grams mole to the minus 1, or which is grams per mole. So that's how we know we can use these units here, as you can see, to work out what the formula is here, because we know that our units, that's obviously providing you know the units are grams per mole for relative atomic mass. You can effectively work out the units and cancel them down to make sure you've got the right formula. So yeah, there we go. So that gets you 1 mark. Right, And then on to the last question. It says, even if the experiment is done very carefully with very accurate apparatus, the answer obtained for the molecular mass of HA is likely to be subject to error. And we need to suggest why. Right. What we need to say really is that even though we've used really, really accurate apparatus, we could get error because we've actually taken loads and loads of different readings here when we've done this practical. So each one have an error or has an error, so that might be quite tricky. Also, we don't actually have a pH reading at 15 centimeters cubed, so that's going to pose a problem because we're just estimating using the other points. We're estimating what that could be. So obviously that's not going to be very it's not going to be very accurate. That's the word I was trying to get. Also, you can say that the acid, perhaps we made that assumption, remember, that the concentration of H plus equals the concentration of A minus. That's an assumption we're making. In reality, that might not be quite the case. It might be very similar, but not exactly the same. And so, therefore, that might knock our answer out as well. So anything like that, I'll write them 3 down anyway. So it gives you, just so you've got a visual reminder. Okay, so there's one. You could put another one. You'll need one of these, by the way. You could put so we didn't take one at 15 centimeters cubed. You can also say that the concentration of H plus is not exactly equal to the concentration of A minus. So anything like that, and that would obviously get you that mark there. So there we go. That's the end of that paper. So it's just a nice short 30-mark paper, but there's a lot of obviously reading, and there's a lot of calculation, and a lot of applying and evaluating and all that kind of stuff as well. So yeah, so that's the that's another CIE paper, I suppose. There are loads of other videos on my channel. As you can see, this is not just the exam technique, it's also the content as well in the videos, and I'm constantly adding things to it and improving it and doing all that. But it's really great if you can subscribe to the channel as well, because the channel really is only worth as much as its subscribers, and you know, it's the whole point of why it's there. So yeah, get yourself subscribed and make sure that you learn lots, and I hope you do well in your chemistry exams and your course as well. Of course, you should really enjoy chemistry, not just because of the exams. But that's it. Bye bye.